Hey robot makers, hope you're having a good day so far. So do you want to recreate the board game Operation but with a Raspberry Pi Pico and MicroPython? And we'll even cover how to make music with a Pico as well today. If this sounds like a show for you, then let's dive straight in. My name's Kevin, come with me as we build robots, bring them to life with code and have a whole load of fun along the way. Okay, let me get over to my keynote and let me get to the front page. There we go. Let me just press play there. Cool. Okay, so yes, this is all about how to recreate the board game Operation, with a bit of a twist. We're going to use a gigantic Pico to help us with this. So yeah, this is inspired by the Hasbro board game Operation. Hope they don't come after me. If any of the legal people are watching, go and watch something else far more interesting. This is just a bit of fun. So yes, we're going to be recreating this, but instead of just using a very simple circuit, which has a buzzer, an LED, and a battery, and when you connect your little tweezers to the surround or the bottom of the operation of the body, it makes the nose light up and the buzzer sound. We're going to take that and do that with a microcontroller instead. So Operation, for people who don't know about this is a game when I was growing up. I believe it was invented, as it says there, in 1964, but we played this in the sort of 70s and 80s, as you can tell from that little clip, that little picture there. So it's a battery-operated game of physical skill that tests the player's hand-eye coordination and fine motor skills. And as you can see, they're invented by John Spinello, who sold the rights, I should say, to Hasbro eventually. He didn't get paid for it either, apparently. So yes, £40 million franchise has spun off from this. So we're going to recreate some more of the electronics and some of the basics of how this works, but with microcontrollers. It's so much fun. So what I did is I designed, just noticed my typo there, I designed basically a mock-up of the person, of the patient. I don't know if he has a name. I'm sure the character actually has a name. And he has various different sort of holes in his body where you can remove bones and things from. I think in the original game, each of these bones is worth different points. So the little I think there's a seahorse or something, isn't it? A little Charlie horse in his leg. That can be worth like 200 points, and his Adam's apple might be worth 400 points, for example. I can't remember the exact values, but I'm not too interested in that. It's more of the how do we build this. So I essentially recreated this in Fusion 360 as a kind of couple of different layers, and I've then made it so that you can laser cut these out and then stack them on top of each other. So there's a piece for the hair, there's a piece for the stomach, the belly, and there's the main body and a table underneath. And it's quite simple to just get all those different holes aligned, paint it, glue it, and away you go. So you can see there the four main pieces: the body, the table, the belly, and the hair. So much fun doing this. So there you go. That's the model as I've created it. Jenny helped with the painting there, getting the colours right. It's just acrylic paint on basswood. Quite simple. I think it's 2mm basswood I used to create this. So the nose is an LED. Now I found these are really great LEDs online. These are 10mm LEDs. So I think the regular ones are about 5mm. It's just like the diameter of the base of the LED. So these are quite large. If I can find an original LED, I can give you a comparison. I've got one in here somewhere. There it is. So a 5mm LED is quite literally half the size. So you can see the difference in size there if I hold these a bit closer. So as with every LED, there is a long leg, which is the live leg, and then there's the short leg, which is the ground. So when you're wiring these up, you just need to remember long is live. The same is true with the tiny ones as well. So when I originally designed this, in that model there, you can see he's got like a tiny one, and there's a little nose surround, the nose holder, or alignment holder, something like that I think I've called it. But we can actually use these 10mm ones instead, which are kind of more authentic to the original design. I've actually not put that in this model just because I ran out of time. More about that later. I'm also going to add in a speaker. So rather than just having a buzzer that buzzes when you make a circuit, I thought it'd be fun to add a speaker that we can play music through, or sound effects. So we're going to have a look at that in the code in a couple of minutes time. So the speaker is actually provided by Monk Makes. They do a really fantastic speaker module. I think it's originally designed for the BBC Microbit. I've got a whole bunch of Monk Makes circuits here. So you can see there, this one, for example, I'm going to spin that one round. There is a BBC Microbit connected into a I2C connector. It simply just plugs in like that. Now the great thing with these microbits, this kind of inspired the thought process behind this project. It's perfectly designed for crocodile clips. I think these also work with banana plugs if you've used those, but I'm a big fan of these crocodile clips. Apparently the correct way to use these is like, rather than it being like that, you actually put it into the hole like so. So it kind of goes at that kind of angle. You can see that. So rather like that rather than like that. Now on these microbits, just out of interest, you can see that there's a whole bunch of, there's like 0, 1, 2, 3 volts and ground on the bottom there. But then there's in between those, there's like much finer grain ones. And if you've got one of these breakout boards, you can actually use all of those pins. So there's quite a bunch of pins there. So it's a different kind of style of microcontroller than the Pico. It uses a slightly different chip, but it's compatible with these crocodile clips. Now, Pimoroni also sell a gigantic jumbo Pico. When the Pico 2 was launched, the RP2350, they essentially stuck a regular size Pico 2 onto this gigantic PCB, which looks exactly the same as a regular Pico 2, just humongously larger. And on the outside, where the regular pins would be, they've got these banana plug compatible or crocodile clip compatible connectors. So I'm going to be using that so that I don't have to do any wiring on this project. I can simply just connect up the crocodile clips and away we go. And that makes it really kind of accessible. If you wanted to recreate this, for example, in the classroom, you can do that too. So the speaker is by Monkmakes and the Pico, the Jumbo Pico, is by Pimoroni. So the circuit is made by essentially connecting one of our GPIO pins to a piece of aluminium foil, which will be behind the patient, behind the table. And when you touch the body through the holes, it will connect the circuit. So the pin will be able to detect that that there is a ground in effect. It'll create like a push button in effect, but we can do that with crocodile clips. So we simply need to attach one of the crocodile clips to the aluminium and one as our kind of probe, our tweezers to grab the bones. So that's kind of how we're going to do this in MicroPython. So there you go, there's the Monkmakes speaker. It's a really nice little amplifier. Surprisingly loud at 3.3 volts. I wouldn't have thought that this speaker could be quite as loud as it is. And it can really be used with any microcontroller. It doesn't have to just be the BBC microbit. It's anything that can connect to these nice crocodile clips. So you can actually get crocodile clips to DuPont pins. I think I've got a few of those. You can just put it onto like a regular Pico, ESP32, whatever you've got to hand. But yes, you do need to provide power to this. You can see that it's got 3 volts and ground coming from the microbit in this case, and then the yellow cable is the kind of GPIO pin out. We can either make that just high or low for very simple sort of buzzes, or we can also use pulse width modulation to do some much more interesting stuff. More on that later. So the wiring for this, pretty straightforward. We've got our kind of crocodile clip probe, we have our jumbo LED there, we have the speaker, and we have the aluminium foil, which is just going to ground, and that's going to be on the back of our model. So very straightforward to kind of put this together. So music on Pico. We can play music through essentially one GPIO pin, and we need to create some kind of library to interpret notes and make it so that we can play music. But it's very, very simple to do this with using something as simple as a buzzer, or in this case, this speaker. So I'm going to show you how we can do this in some code, and we're going to code this in a second live. So the code on the right hand side there is essentially how we can play a tone. So we can set up the pin as a pulse width modulation. I'm on pin 15, which on the Pico is the very bottom left pin. We can set the frequency, and we want to be able to set the duration of the note as well. So this will define how long that note plays for. So we can set the duty cycle. That's essentially going to be fixed. In a sense, it can be used as volume, but really we're not dropping the volume, we're just dropping how long that frequency is being played for. So by default you can have, I think it's 65,535, something like that, which is the full byte worth of information. That's for the duty cycle as a unsigned 16-bit integer, or we can have half of that duty cycle for kind of half the volume. So we've just used that half volume there at 32,768 as the duty cycle. That sleep basically just says just sleep for the duration that's been passed in. That's how long the note will play for. And then we then set the duty cycle to 0, which essentially stops it from making any sound. If we don't do that, it'll just carry playing that note forever until you remove power. So that's how we can play a tone. So to pass in a specific frequency, we can then just say play tone 440, 0.5, which is how long we want that note to play for. So on a piano, 33 hertz is C. It's a very, very, very low frequency C. And essentially, if we just multiply that by 2 each time, we'll get different octaves. I can show you that on a slide in a second. But if you want to grab this code and play along, you can go to github.com/kevinmcaleer/operation_pico, which is where I've stored all the code that you're going to be seeing today. So I've got a quick how sound waves work and how we can reproduce this in code. So you can see there, for tones, we need to first understand how sound waves work. So the amplitude is the volume of the sound wave, and the cycle is how long it takes for it to do one up and one down wave form. So that's essentially one cycle, and one cycle equals 1 hertz. So 1 cycle per second is 1 hertz. We talk about frequencies being in hertz or kilohertz, for example. So if we want to do this with pins, GPIO pins, we can essentially make a pin go high and then make the pin go low to make that kind of a square waveform. That will sound quite harsh. We can do some things much better with that if we want to sort of soften out that waveform. But essentially that's how we can do the same thing just by doing a pin value 1 and pin value 0. That'll make it go up and then make it go down. We can do that very, very fast with pulse width modulation. So you can see that C is 33 hertz, C sharp is 35 hertz, D is 37 hertz. And if we multiplied that C by 2, we would get the next octave up. So it doubles each octave, which is just an interesting physics of how this sound works. So each note corresponds to a key on the piano. We've got C there as our first white key. C sharp is the next black key up there. We can also play those as flats as well, but in this case it's easier just to say D flat is also C sharp. It's the same note. So that we're just going to stick with using sharps rather than flats. You can see there middle C, C4 as it's known, is 261.6 hertz. So notes and octaves. So like I said, if you look on this little table that we have here, this little list of a dictionary of notes, C3 is 131 hertz. If we look at the very bottom, C4 is 262 hertz. So it's double what the previous octave was. So octaves have notes that have twice the frequency of the previous note. So that'll come in handy when we're creating something to actually play our notes. So on this piece of code here, and I built out an entire music library that we can use to make music on our Pico, or anything that runs MicroPython, to be honest. So this note frequency will take in a note and it will take in an octave. And this is how we can store our notes to make up a piece of music. So on here, for example, C is 261.63 hertz, C sharp is 277.18 hertz, and so on. And we can essentially use that as a base frequency. It's a couple of octaves up, so we can minus it by 4 to get the right octave, and you can see there we times it by 2 each time to get the next octave up. So we can sort of normalize it, figure out where the base frequency is, and then as we pass other notes in, we can say what octave it is, what part of the keyboard is that going to be played from. And then how fast those notes play. This will be useful when we actually want to write some music using this library. We'll want to know if there's a bar of music, and this is how we write it down in musical score. A bar is between those two lines there, and that represents how many notes will occur in that particular time sequence. So we can have a semibreve, a whole note. We can have a quaver, which is like an eighth of a note. So there's 8 notes being played in that one bar. We can have minims, which are half notes, semiquavers, 16th of notes, crotchets, quarter notes, demi-semiquavers, 32-second notes, and so on. So essentially, if we just pass in a 1 to our music library, it'll play 1 note for a bar. And we can set what the tempo will be as well in our music library. So this is how we can create music. So there's the entertainer, D4 for 1 bar, D sharp 4 for another bar, E4, C5 for 2 bars, and so on. And it'll essentially take in that dictionary of notes. I think it's a list of, yes, a dictionary, sorry, of notes. We can pass that in and we can say play entertainer, and it will understand how to interpret each of those notes and play them at the correct pitch and the correct tempo. It's surprising how good that actually sounds. So to use our music player, we simply need to import machine so that we can use pins, import music, which is the code I'm going to show you in a minute, import music player, and then import the tunes, which you've just seen on the previous slide, which has all the different notes that we want it to play. And then we can simply say m equals music player, pass in the pin that it's going to be connected to the speaker, in this case pin 15. We can set the tempo, which is how many beats per minute, and then we can say play tunes da-da-da-dum, da-da-da-dum, and then we can say stop so that it doesn't play any of the sounds, it'll just drop that volume of that. So if you like what I do and you want me to make more of these kinds of videos, please drop me a like. Let me know in the comments if you've ever played Operation, if you have a Pico or an ESP32 or a microbit. Let me know what kind of microcontroller you use. And if you've not subscribed to this channel already, please consider subscribing. It means so much to me when people do subscribe, and that'd be really great if you've not already subscribed, if you do that. And I do go live every single Sunday, come what may. More about that later in the live chat. 7 o'clock every single Sunday. So if you want to come and hang out in the chat, you can do that there. So let's look at how to play notes on the Pico. So what I'm going to do is I'm going to break out now into, I'm just going to put it onto me for a second, get my notes handy. And I'm also going to get my code on that screen so I can see what we are doing. So let me just move that around on my second screen. And we're going to do a speaker test first of all. So I'm going to load up Thonny. I've got Thonny over here, and what I'm going to do is I'm going to go to this nice piece of code here that's just waiting for us to fill in some information. So the first thing I'm going to do is say from machine import pulse width modulation and also pin, because we're going to need those to be able to use our GPIO pins. So PWM is going to be equal to PWM, the class, and we're going to pass in a pin, and it's going to be pin 15. That's what I got my speaker connected to. And I want it to make some kind of tone just to make sure I've got it plugged into the right pin and that the crocodile clips are all connected and so on. So if I do PWM.frequency and I make that 1000, and I do PWM.duty, and this is going to be an unsigned 16-bit integer. That's what that means there. So we're going to pass in 32768, which is kind of half volume, and I'm simply going to print out as well PWM initialized on GPIO 15 with 1 kilohertz. I think it's small k, capital H, kilohertz. Hertz was a person, wasn't he? Frequency for 50% duty cycle. Okay, so if I now run this code, you may or may not hear a buzz as I do this. Yep, so it's now done that, and I've not told it to stop. So what I'm going to do is quickly add in there a second bit, which will make that 0. And I also need to do import from time import sleep. And I'll basically get it to do that for 0.5. Let's run that again. Always have that stop. So there we go, let's try that again. There we go. So we've now made a beep function. We could wrap that in a function and just call it beep and call it quits. So let's do that. So if we say def beep, and then we just indent all that there, we can then just say beep, and it will beep. And if we want to do beep twice, we could just say let's just do beep beep like that. So you don't hear a pause between them. We'd have to put a little pause in ourselves if we wanted to do that. So you get the idea. We've got the speaker plugged in. Do let me know if you couldn't hear that actually on the live stream. I'm not sure just how clear that was, but I can hear that quite loudly next to me. It's surprising how well that speaker from 3.3 volts can output sound. So yes, it does indeed, Vince, sound just like bias beep codes. This is essentially how they do that through very, very simple hardware. So that's how we can test out our speaker that's connected up. Next, I need to test out if we can play some actual notes. So rather than just a beep, we want it to do a specific note. So let's do that on a new piece of code here. So let's do from time import sleep. Let's get that in first. And we will also say buzzer, call this speaker, I guess, buzzer equals machine.pwm machine.pin. Great, loud and clear, everyone's saying there, thank you, Marlene. Pin 15, and we're going to create a new function that's called play tone. I'm going to pass in the frequency that we want to play and the duration. So let's do that. So buzzer.frequency is going to be whatever we pass in as the frequency. The duty cycle, so buzzer.duty, that's the unsigned 16. That's going to be the same that it's been on the other one, 32,768. And then we're going to sleep for whatever the duration is that's passed in. So it'll carry on doing that note until we then drop the duty cycle back down to nothing. Like so. And then we'll just do another quick sleep for half a second. So now in our main block of code down here, we can say play tone, and we can pass in 440, and we'll do that for 0.5. So let's just put a little note there. That's an A note, and that's in the 4th octave for 0.5 seconds. Let's do another play tone. This one is going to be 523, again for half a second. This will play a C5 note for 0.5, and then we'll do one more play tone, and this will be 659, and that'll be 0.5 seconds as well. So that will be an E5 for 0.5 seconds. Right, let's see what this sounds like. It should play. Oh, playtime is play tone, sorry. So it should play 3 notes. There we go. Now, if we had to write music by doing play tone and specifying the frequencies, that would be really, really hard work. So it'd be much better if we can have some kind of library that can map notes as we know them when we're writing music, and have the play tone figure out what that is in frequencies. So that's really what we need to do as a next step. There's another thing on here that's a good practice as well, which is buzzer.deinit, and that will deinitialize and clean up the pulse width modulation. It's just best practice to do that. Okay, so let me go to our next piece of code, and we want to play some music this time. So I'm going to show you the music library in a second. I'm going to show you how to use it first. So if we say from music, so this isn't installed on the Raspberry Pi Pico. This is a library that we will have to copy across. You can see there's a piece of code there called music, and our Pico has this installed as well as a little library. So we will need to make sure we copy that across if we want to make this work. So I'm going to import music player, which is a class I've created, and from tunes, which is another. Let's have a look what's inside tunes. So tunes is a list of dictionaries which has entertainer, prelude, ode, Nyan. There's a lot of detail in Nyan. Birthday, jump up, jump down, power up, power down, Nintendo on. We'll play each one of those and we'll see how that works. But you can see how this is formed. So there's a name, and then within that name there is a dictionary. Or is this a list? This is probably a list actually. So it's a dictionary of lists. Yes, so the dictionary is the curly braces, the list is the square brackets. So each of these is essentially like a separate item within our list. So G4:2 is to play the G4 note for half a bar, G4 for full bar, and so on. We've got some there, D#4 for 8 of a bar, so that'd be really quick. either really quick or really long. I can't remember which one it is. So that's the tunes. We can import that into our code, and we've got access then to all those different pieces of music. So let's import tunes. And it's uppercase because it's a constant that isn't going to change. So let's say example usage. So M equals music player, and we need to pass in what pin our speaker is connected to. So machine.pin, pin with a capital, and then it's on pin 15, that's where our speaker is. And then m.set tempo, so how many beats per minute do we want? So BPM equals 120 beats per minute. And then m.play, so we can then pass in tunes, which is our list dictionary of all the different things, and we can pass in there da dum, there we go, like so. And then we'll have an m.stop just to make sure, just in case it crashes or anything like that. So let's play this and see what this sounds like. Oh, there's a beats per minute, not BMP. There we go, beats per minute. So I can just say click, 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 click. It doesn't sound like it's putting anything out there. So that's interesting. I wonder why that, what have I done wrong there? I'm just going to make sure my cables are connected all right there, and I'm also just going to run that code just to make sure, yep, everything's fine there. So let's see what's gone wrong there. So we're on pin 15. It just didn't sound like the right tempo, that. So what I'm going to do, I'm going to try a different piece of, let's try Ode and see if that sounds any better. That doesn't sound right. What have I done? Let me check. Let me make sure that I've got all the latest music uploaded to here. Just do that again. Right click, upload. If it says it's the same size, smaller size, I must have changed the code. So what I'm going to do, I'm just going to check through my music and make sure there's nothing in there that doesn't need to be. It might be those print statements might be messing it up a little bit. So I'm just going to echo, I'm going to comment out any print statements. Print statements take quite a bit of time to print out, and they can actually interrupt with your code, particularly if it's something that has to happen very, very quickly. So I'm going to do that there. I'll leave in the error ones, we want those, but we don't want to have these other ones. Let's try that. So let's get rid of that. I'll go through this code in a second to explain how this works as well. So now that we've updated that, let's copy that across to the Pico. And let's try running our test code again. It's just doing a click sound. So it looks like something has gone wrong there in the, is it the volume? Let me check. It can do this if the volume is incorrect. So let me just check to see if I've got something that actually changes the volume. Let me do a set volume in there in case that's what it is. So m.set volume, let's have that as 100. I had this working before. BPM slow down. Let's try 60. I think it's to do with the pulse width modulation. Yeah, I don't think it's the BPM. I think it's to do with the pulse width modulation. Let me just see if we can troubleshoot this live on this stream. That's frustrating. I did have this all working before, and then obviously I've changed something as I was trying to make something better, and clearly that's messed something up. I think it's to do with the volume. That's my instinct, because if the volume is changed, it's not true volume control. Essentially we're messing about with the pulse width modulation, so it's probably to do with, let's see, the volume is set to 100 by default, so unless we set it specifically it should be fine. But the piece of code here, this might be the thing that's causing an issue. So what I'm going to do, I'm just going to go on to GitHub. I always upload my code to GitHub, and every time I change it, I check in like a new version. And that means if I do something where something was previously working and now isn't working, we can quickly get back to where we wanted it to be. So I'm just going to quickly find the line of code where I messed with that. And I think essentially what I want to do is just get rid of that duty thing. Let's just try this. Duty equals 65,000. We had 32,768, didn't we? Let's try that. And I'll just comment out this one. I've got this gut instinct that it's that line there that's causing the issue. So let's try that. Upload that. Because like I said, it doesn't really truly change the volume. It just messes with the pulse width modulation, so there isn't as much sound coming through. Let's see if that's any better. I knew it was that line of code. Recognise that? That's Ode to Joy. Let's try da-da-da-dum. Okay. We don't need to do that. Let's just play. So I think there's a rogue note in there actually. That up one, that didn't quite sound right, but that's da-da-da-dum. Let's play Nyan Cat. I think this goes on for quite a while. Kind of right. Right, let's see what else we've got. We've got the Entertainer. Let's try Entertainer. I did kind of rush these together. Let me just press play on this one. That's kind of right. It kind of goes up and down a bit in odd ways, but you can kind of hear it. So Goldfinger's asking a question about the Monk Make speaker board. Does it have an amplifier or is it separate? So it's all built into the actual board itself. It has an onboard amplifier, and that's what the 3.3 volts and ground in is, and the yellow cable that we had before. I'll show in the overhead if we can actually go to that. So you can see there's the speaker. The yellow cable is simply connected to, this is kind of upside down, so that's GPIO 15. And the little power light there is showing you that the amplifier is switched on. It's why it's so loud. So let's get back to our code. So that was the Entertainer. Let's see what else we have on here. We've got Prelude. Let's try Prelude. Is anybody old enough to remember when Windows used to have like MIDI files? It's essentially what these are, but without the MIDI part. Yep, so it's kind of a truncated part of that. So we played Ode. Let's play Birthday. I wonder if I'll get a copyright strike because it's is it Warner, Time Warner who owns the copyright? So I'm going to get a couple of bars of that. And what else have we got? So then we've got these up, down, power up, Nintendo on. The Nintendo on one isn't great. I was trying to make it do the when you switch on your Game Boy kind of sound, but let's do like power down. Let's try that one. Sounds a bit weird. And then let's do power up. That's quite a good one. So what I'm thinking is we can use one of these, because it's just 5 lines of code in our operation, so that when you switch the power on, it will play a little tune, and you know that everything's ready to go and you can start playing. And we want some other kind of sound, some kind of buzzer sound when you touch the patient and you know he gets the electric shock or whatever. We want some kind of indication there and make the nose light up as well. So that's how we can use this library. So let me just take you through the actual music code itself. So we've got these defaults. These are all in uppercase because they're constants and we want some kind of default value. So the BPM 120, ticks is 4, octave is 4, and duration is 4. And then we've got this articulation, the gap between the notes in milliseconds. Articulation, and then we've got the default pin 15. We can change that to be whatever we want. And then we've got the main music player class. So this init function, this double underscore init double underscore, takes in a pin. We can pass in the default pin so that we've got a value if the user doesn't provide one, and we've got this volume, which to be honest, ignore the volume thing. That was a bit of a failed attempt to try and give something a volume where we haven't got very advanced sound output. So we're going to create a self.pin, so this means that within this class the pin variable will contain the machine.pin for the pulse width modulation. The beats per minute is going to be whatever the default beats per minute is, and we can set that by just doing like the class name dot bpm, as you've seen. The ticks is default ticks, the last octave is the default octave, the last duration is the default duration, and is playing will be set to false. We can use this to internally check whether there's a piece of music being played or not. And again, we can ignore that volume for now. That was kind of a failed attempt to make that work. So setting the tempo, we can set the beats per minute. We're going to pass in none to begin with and ticks none. If beats per minute is provided, then we will say self.beats per minute equals whatever is passed in. If ticks is provided, then we'll also update ticks as well. We can get the tempo, that'll simply just return the tempo. We could actually improve this further by simply, instead of having a function for this, we could just have a property. We could have a property decorator and also a setter that will set the values as well, but for now that's fine. So we can ignore the set volume, that didn't really work. Play frequency is essentially the code that we created at the beginning of this. We're going to set, if the frequency is 0, then we're going to set the internal frequency to be 0, the duty cycle to be 0, so it's going to mute it if we don't pass in a frequency. If the pin.frequency, sorry, the self.pin.frequency is going to be set to whatever is passed in as the frequency. We're going to make sure it's an integer, so we cast it there. So if it's passed in and it's got like 1 point whatever, it's a floating point number, we can essentially chop off those. We're not going to be, you can't really hear that point something of a frequency, so we're going to chop those off and just pass that in. We're going to set the duty cycle to just be half. That's where the volume thing wasn't working before. And then we're going to set the duty to be whatever the duty is there, which is, we've just set to be that 32768. It just needs to be an unsigned integer between 0 and 65,500 and whatever it is, 36, 35, something like that. Then we need to play the note. So once we've set that duty, it's going to make the sound, and it'll make that sound until we set the duty to be 0. So that sleep will be whatever the duration is in milliseconds that we've passed in there. So then the note frequency is what multiple of the base frequency of these is it. So if we pass in a C, we want to multiply that 261 by whatever value is passed in, whatever octave is passed in. So that's what this piece of code here does. What else is there? So then we have the play the note. So this is where we pass in a list of all the notes that we want it to play, and it'll work its way through that list. We can include a wait and a loop as well if you want it to play multiple times. We can have that wait of how long does it wait before in between playing it again. So while self is playing, then go through for each note. For note in notes, which is passed in. If not self is playing, break. So if we're not playing anything, stop. If is an instance of a string, this is a bit of error checking just to make sure that if what's being passed in is actually a string of characters of notes and numbers. If it's not, we want it to basically say there's an error parsing that note. If it does work, we want to say notes and duration equal whatever parse note string returns, and that's a function that we've got a little bit further down, so we'll have a look at that in a second. Otherwise, if that fails, if it isn't a string, we'll just say invalid note format for note. The frequency will then be whatever the note frequency of that specific note is that we're going through. So note 0 and note 1 is what we're setting that frequency to be. If the frequency is, if there's a frequency passed in, so if that is a valid value, then the duration equals 60,000 divided by the beats per minute times by the duration, and then divide both of those by the self.ticks. So ticks is kind of how granular you want this to be. So that's quite an interesting little piece of code there. And then self play frequency, we pass in the frequency, the duration minus the articulation, and then we sleep for that articulation time as well. So that's the gap between the notes. Otherwise we say skipping invalid frequency for whatever note. And if it's not a loop in it round, we stop at that point, otherwise it'll carry on forever. And then at the end of that we say self is playing equals false, so we're no longer playing any music. Stop simply just says is playing is false and literally turns off the duty cycle to 0, so there's no sound coming out the speaker. And then this parse note string will kind of unpack a note such as C4:4. So that's the C in the 4th octave. We want that to play for a quarter of a bar, I think. So you can see there, note an octave equal note dot split string. So this is going to split into two. So the C4 will go into the C4 will go into the note octave, and the duration will go into the duration part. So that's how we can split out between that colon and get rid of that colon. Duration also needs to be an integer, so we need to make sure that that is an integer by putting int in brackets. That makes sure that definitely is an integer. It casts it. And if the length of the octave note is less than 2, or it's not, or note octave minus 1 is digit, that's essentially, if you've got your pound sign, your hash sign, your sharp sign in the wrong place, this is where this will catch it. This caught me out quite a few times. So if you've got like C sharp 4 rather than C4 sharp, that's where that will mess up. Octave is the octave, so it's the last character. It'll basically just pull out that last character from the note. So note is made up of 2 characters. The way that we get the last one is we say -1, so it kind of reads from the right hand side. So it'll grab that 4 character there, so it's the 4th octave. And then we can extract the note. Note is note octave :-1, so that's like the first, all characters apart from the last one, essentially that means. So we should end up with a C or a C sharp or a D or a D sharp and so on. I'm not sure what the R is, we should probably get rid of that. It might be a break or something like that. So what else we got there? We have, if note is not invalid note, then we can just raise a value error saying invalid note. Otherwise we can return the note and the octave and the duration to the thing that's actually going to play it. So, and then we got the these other pieces of code, you can pretty much ignore them. So play Nintendo on, it was me trying to make a Nintendo on sound, and play buzzer is actually used in our operation game. So this simply just makes a sound. It oscillates between a couple of frequencies and just makes a bit of a buzzer sound. That's it, that's our music library. That's what we actually need to upload, as well as the tunes library to our Raspberry Pi Pico. So let's have a look at the operation game itself. So we've got a couple of components. We've got the nose, so that's an LED. So we want that to be on pin 0, and the pin out is there. We have the contact, which is when you make contact with the little tweezers. So that's on pin 1, it's a pin in, and we also want to pull it up because we're going to be detecting whether it's grounded or not. So we need to have a pull-up resistor, which we can do internally in the chip. Nose value is going to be 1, then we're going to sleep for half a second, and then nose value be 0, and that'll just make his nose flash when we switch it on. And then we can do music player on pin 15, and that'll make it ready for us playing some music in a second. Now the check probe function is going to test whether when we press the crocodile clips to the back of the patient, we're kind of connecting the circuit, we want to make the nose light up, and we want to play that buzzer sound. So if the contact value equals 0, and it will only get that when we've touched the ground, nose value equals 1, music play buzzer for frequency is 100, duration is 500, so half a second, and the buzzer rate is 50, and we want it to sleep just for a fraction of a second. Otherwise, we want the nose value to be nothing, we want it to be off, and we want the music to stop as well, just in case it is playing. And then we want to check that every 10th of a second. And when we switch this on, we'll do the play Nintendo. It doesn't sound like a Nintendo, it just sounds like a weird sound. We can actually get rid of that set volume because that doesn't actually work. We will set the tempo to be 120, and we will play the power up kind of sound, and then we will stop the sound. And then we're just going to run through the check probe, and it's going to run through that until we stop the code. So let's go over to our overhead camera. In fact, we can probably do it like this, and I can run this code, and you can see, there we go, it did that weird, and then so if I now get the little tweezers, and you have to imagine that I've actually 3D printed some bones out. Maybe this is going to be one of his bones there. So can you see that? Let me go full screen. So I can easily grab that circle thing there without making any contact, like so. But if I had to reach down in here, you can see that his nose lights up when I make contact, and it kind of makes a sound. Let me know if you can hear that. And really all that we're doing is we're just making contact with the aluminium foil which is on the entire back of this. You can just see there, that's just the LED as well. So when I make contact with any of these back pieces, we get the nose. Now we could take this further, we could have a little counter up there to show how many times you've touched this. We could have a counter. We could have, if we wanted to be really clever, we could have little lights that light up each one of these little sections, and as you remove pieces we can perhaps switch those off. If you press something, maybe we can make that section light up red. So there's lots of things that we could do to really take this project kind of to the next level. Lots of different things there. So let's go back over to here. So I wanted to share with you a couple of new products that we have on the kevsrobot.com store. Grab my little supply over here. So we have the Robot Maker Almanac. So I'm going to be showing you this every single week because I've put so much time and effort into this. I think I actually started making this 3 years ago, and I've been building out all the different bits of information that are actually in here. So there's so much information about all the different microcontrollers that are in there. I can show you the content page there, but you might be able to read that very easily. So we've got Raspberry Pi Pico, Microbit, Arduino Uno, Arduino Nano. We've got the HC-SR04, which is the ultrasonic rangefinder, M5 Stamp Pico, M5 Stamp Core. We've got the Raspberry Pi 2345 and 0 boards. I need to update this for the Raspberry Pi 500 as well, because it's got the Pico 23450 and 400. The MX1508, which is a motor driver, L298N, which is another motor driver, and then all the dimensions for each of those components. So not only do you get the pinouts for each of them, for example, there's the Uno 3 with all the pinouts, you also get all the dimensions of each of them. So really handy if you're actually building a robot and you just want to have that information to hand without having to find it and losing your place. And then if you want to write some notes, drop some inspirational ideas for your robots, you can do that with one of these maker notes, and has a inspiring note on the very back there that says, now go and do something, go and make something. So these are all handmade by me in the UK. So I don't think there's anything quite like this available on the market at the moment. And you can get all that information online, probably for free. It's just all in one place. So I've made that really easy for you. It's an absolute must if you're a robot maker. And I've also purchased 100 of each of these PCBs that we have. So there's the Pico Tamachibis, there's the gamepads. I'll be doing a show on the gamepad, another one very soon as well, just to show you how you can use that with some other projects. And there is also the servo helper, which if you work with servos, you'll probably know that often you need a separate power supply than your microcontroller power supply, and this makes it really easy to sort of manage all that. So really cool. So if you want to join our Discord community, we have a thriving Discord community. If you head over to kevsrobots.com/discord, you can get yourself a free sign-up link there and join the conversation that's going on over in Discord. You can also share projects that you're working on. It's a great place to get answers to any kind of techie questions that you might have with code and so on. And if you want to follow me on social media, I'm on all the social media platforms. I'm at Kevin McAleer at threads.net. I'm on TikTok at Kevin McAleer 6. I'm on Instagram at Kevin McAleer. I'm on X as at KevMac. And I'm on Mastodon at kevsmac at mastodon.social. And I'm also on Blue Sky at kevsmac.bsky.social. I think that's my favourite place to hang out currently, but I do post all the places on there. And if you want to join me and get your name in the credits, then you can do that very simply by going to kevsrobots.com/coffee, and you'll find all the information that you will need there. You can also do a super thanks if you're watching this on replay, or a super chat if you're watching this live right now for the price of a coffee. If you want to join the YouTube membership program, you can click on the subscribe plus button if you've already subscribed to the channel underneath the main player, or you can go to the Buy Me a Coffee site and become a member there as well. So there's lots of different things. I'm just on a note there from Mike. Mike says, nothing like maker notes. I'm talking about the Robot Maker's Almanac. There's nothing like that. No, the maker notes are very much like Aaron Draplin's field notes. They're very much inspired by that. But he doesn't make his own by hand. I think he has a factory to do that for him. But these are very much inspired by field notes, but made in the UK. So yes, thanks for that note, Mike. Nothing like Robot Maker's Almanac. When I was little, they used to have I think it was like a farmer's almanac, and it had all kinds of like horoscopes and astrology things in there, things that are probably not very, I wouldn't take very seriously nowadays, but it had like really long range weather forecasts, as well as lots of other interesting facts and figures. And I always loved this thing. It came out once a year, and I think I bought it every single year. And the word almanac sort of lived in my head rent free, as they say. So I needed to do something with that. So let me just click on the next button there. So yes, let's give a shout out to the people who are supporters to the channel, which there are myriad. So on the left hand side here, we've got Cody Marie bought a coffee. Thank you so much for that. Really do appreciate it, Marie there. Doug Topping bought 3 coffees, and Johnny bought a coffee, I think, in the last month. So that cycles around every month. People will drop off there if they've not bought a coffee in the last month. And then people who have joined the Buy Me a Coffee membership. So we've got Marie TKD, we've got Andrew, we've got Shemi, Jeff, Dian Corty, Marling and Tom. And then on the right hand side over here, of course it's mirrored for me, so I'm pointing completely on the left side, we've got Khan, we've got Hybrid Robotics, which is Dale, we've got Marie, Michael, Steve, Ford, Bello, Orkshrad39, Littleback, Paul, Johnny, Prem Kumar, Stephen, we have John Paul, Alistair, Cassie, Tinkering Rocks, Johnny and Tom. So thank you so much for subscribing. I can't tell you how much it means to me that you continue to support my channel as well. I really do appreciate every single one of you. And if I just go back to there, yes, that's everything I wanted to cover off on today's show. So it's at this point in the video, YouTube over here will recommend another video for you to watch from the over 400 videos that are now on the channel, and hopefully you'll find one of those as inspiring as this one. So thank you so much for watching, and I shall see you next time. Bye for now.